Okay, so we derived this equation, which we called the time-dependent Schrodinger equation, and that's the solution that determines what psi is, what this function is that describes the particle. But that's a difficult equation to solve, and so it would be nice if we could make our life easier. So we used, right, so we can make our life easier if we can break up psi into a space part and a time part, and we did this when we had this expression where we assume this solution, and I can write e to the I k dot r minus omega t by breaking up the space part and the time part and writing two exponential functions. Of course, this reduces to the function that we had before by the rules of exponents, right? So I can break it up like that. So this was a free particle, but we argued that, so this term was missing, but more generally, if we don't have a free particle, we have some function, some potential that's not zero, then the time-dependent Schrodinger equation looks like that. But the point was that when we had a function like this, right, so this can be written as, let's say, a part that involves space. Let's call it psi n for reasons that we'll see in a bit, and a time part, right? So this is the psi n part, and this is the psi t part. And the solution has these two things multiplied by each other, right? When we put these into this equation, this part acts only on the space part, this part acts on the time part, and we end up with two equations that give us a number. So this acts on the space part, which I call psi n. If I have this term, then it looks like that. And so I have, let's call that an En, whatever the energy is. I'll get that equation. And the time part obeys the second equation. But both of them give me back the same right-hand side as we've seen before. So the point here is that breaking this equation up into these two parts allows us to then reconstruct the solution by multiplying these quantities. And more generally, this is, we can say that the solution can be written as a sum of these kinds of solutions. So we can imagine it could be an infinite sum. So the energy, right, so we could have different values of energy. And so the question is also, what is the spectrum of energy? What are the possible values of energy? It's not just one value of energy. And so the N sort of labels the different possible values of energy. And this would look like a sum. Sorry, my pencil is falling apart. I'm going to have to use a pen here. So this would be Cn times the space part times the time part, but the time part is e to the minus I omega t, or e to the minus I En over h bar t. So let's just write that out like that. Or we can just sort of write this out term by term. Plus C2 psi 2 e to the minus I e2 t over h bar plus dot 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 and so on. That's a sort of a general solution. I can reconstruct the entire solution by adding these individual terms, and the point of this solution is that we can think of it as the solution for a vector written in terms of a certain basis. And so there are some properties here. So the psi ends are orthonormal, which mathematically looks like this. This is a very abstract idea that we can make less so. So this is equal to 0 or 1 depending on whether these functions obey the following. So if they're the same, if psi m is just psi n star, then we'll get 1, otherwise we'll get 0. And so this allows us to get these coefficients in the expansion. And there's a very intuitive way of understanding this expression. Let's think of a vector that's written in terms of x, y, and z coordinates, so that in x, y, and z coordinates we have an x component, which is a b component, or a y component, which is b, an x component, which is a, and a c component, and a z component, which is c. So it would look like that, right? It has components a, b, c in Cartesian coordinates. And we can say, well, how do we get the various coefficients? Well, to get a, we need to do a dot product between the full vector and I hat. So I would say the coefficient C1, which is, of course, a, is equal to I dot the full vector. And, of course, that gives me I dot a I hat plus b j hat plus c k hat, but the only non-zero contribution is the first term, because I dot j is 0 and I dot k is 0, so I get I dot I is 1, and I just get the a. So I get the C1 is equal to a. It's very similar here, except that the operation isn't under the dot product, it's under integration that we get the orthonormality condition. And so this is going to make it very straightforward, because we will be able to write any function in terms of these sort of basis functions, if you will, right? If we solve this equation, we'll be able to get all of the possible psi n functions associated with different values of energy. Each psi n will have a different value en, and we can sum them all up together in this way to get the overall solution.